Technology exhibition. We're in the beautiful RDS Concert Hall celebrating the 60th anniversary of this unique and wonderful exhibition for young people on the island of Ireland. And I'm absolutely delighted to be joined by Professor Lorraine Hanlon, who is the Director for the Space Research Centre at UCD and Head of Astronomy, and Dr. David Murphy, who's a science researcher but also systems engineer for EIRSAT-1. This is really exciting, folks, because we're talking about Ireland's first satellite. So I'm delighted to have you both here on the stage with me today. And David, I'm going to go with you first. I mean, it was well promoted, and it was fantastic to see the response from the public. But maybe can you give us a little bit of detail? Just what is EIRSAT-1? What does it actually do?
So, okay, the first thing I should say about EIRSAT-1 is that it's Ireland's first satellite, which is kind of a big deal.
Yes.
It's really, really exciting. But what EIRSAT-1 is physically is a 2U CubeSat. So what is a CubeSat? A CubeSat is a very, very small satellite. That, as the name implies, it's a cube. So it's 10 centimeters by 10 centimeters by 10 centimeters. And EIRSAT-1 is a 2U CubeSat. So you get two of those cubes, you stack them on top of each other, and that's the size of EIRSAT-1. So it's a very, very, very small satellite, but it's packed full of technology. It has everything that goes into a big satellite, which doesn't make it easier, it makes it harder, if anything. So that was a challenge, but it's got three really, really cool experiments on board. So one is GMOD, is a gamma ray detector, which we developed in our group, and that's going to do all sorts of really, really interesting astronomy, and it's going to pave the way for future experiments in astronomy as well. The next is called EMOD. It's a thermal materials experiment. So if you ever see a picture of EIRSAT-1, you'll notice on top it's got this sort of Battenberg, this black and white checkerboard. That's EMOD. So these are these materials made by an Irish company in Bio, and they're called solar white and solar black, and they protect the spacecraft from thermal loads from the sun and such. And we're testing those out on EIRSAT-1. And then the third is called WBC, or wave-based control. And that's actually an algorithm. So that's a software payload, and it's going to control the direction that EIRSAT-1 points in space. And it's hoping to do that in a really, really efficient way that we can apply maybe in future to flexible spacecraft, and it will work particularly well, we hope, on flexible spacecraft.
Oh, wow. And from the observation point of view compared to other land-based observatories, I mean, this is a relatively small instrument, the Gamma Ray Observatory. I mean, what do you hope it will achieve? I mean, are you expecting to really achieve much, or is this a test bed?
So I guess the first thing you need to know about gamma ray astronomy is you can't do gamma ray astronomy on the ground. The gamma rays don't reach us on the ground, which as humans is fantastic news, because gamma rays, as you know, are very, very dangerous to humans. So we don't want them on the ground. We're happy to have them left in space. But as astronomers, it's kind of bad news, because it means we have to put all of our instrumentation in space if we're going to be able to observe it. So compared to ground-based observatories, that's the big thing, right? It has to be small enough to get it into space. Yeah. But these gamma ray bursts that it's going to study, they're incredibly bright, really, really bright. For a couple of seconds in some cases, or milliseconds in the case of very, very short ones, they're brighter than every other source of gamma rays in the sky combined. So basically they're like a big beacon that's shining really, really brightly, saying, here I am. And that's why GMOD is so effective despite its size, because the thing that we're looking at basically just takes its attention.
Oh, fantastic. And Lorraine, I suppose, I mean, this is Ireland's first satellite. I mean, what is the significance of this to you from the future of Irish research and the Irish space industry? I mean, can you maybe explain what this means for Ireland?
Sure. I think the first thing to say is that there's been a lot of space research in Ireland since the beginning of the space era, and I think that's paved the way for us to be able to do this now. But we're used to thinking, as you heard from David, of satellites as being really huge, international projects. You think of the Hubble Space Telescope, and that's our mental picture of these telescopes for science and astronomy. And from many science questions, we need that big instrument to be sensitive enough to pick up the signals. But there's definitely a growing usefulness for smaller satellites like these CubeSats. because the technology is miniaturized so well now. You know, our phones have these incredibly powerful cameras, so a lot of that technology is coming to playing a part now in the space sector as well, and that means that you can have these small satellites that are actually really useful for doing science in lots of different areas, not just our field of astronomy, but also looking at Earth and looking at climate variables, at you know, damage that is caused by flooding, for example. So there's a huge range of applications, and I think that's why for science they're exciting, because smaller countries and smaller research groups can really get hands-on and develop the capability that we have now through the students who have built the satellite and are now operating it from UCD up the road from us here. And also that capability is so important for industry and companies and businesses who want to use data from space and maybe even get their own data from space and maybe even build their own technologies for space. So what we have now is a really expert pool from the students who have worked on the spacecraft to support Irish industry into this hugely growing sector, not just in Ireland, but globally. It'll be a $1 trillion industry in the next 15 years or so, according to the forecasts. So really, we can't afford not to be part of that story.
Fantastic. And you mentioned capability and skills. Can you give me an example of what skills do you think were developed whilst designing? Maybe for both of you, if you want to go first, Lorraine.
Sure.
I'm sure there's a lot of new skills.
There's a lot. So much planning has gone into this spacecraft. And we worked with the European Space Agency, who were our partners for this mission, but all of the students were based in UCD, basically, and all from all over the world, but studying in UCD. And so planning, what do we want to do? Why do we want to do it? How are we going to do it? What materials do we need? Can you use them in space? There's a big long list of things. No, you can't use that in space. Oh no, that'll crack. Oh no, we have to. So, and we're at the cutting edge in materials terms, understanding, you know, what the performance will be in space, which is a really punishing environment for any technology. So testing and testing and testing again. I'm sure David will testify to the pain, no pun intended at that. Dealing with launch brokers, dealing with the government, all that learning and expertise that we really had to build out from a very low understanding, because we'd only ever looked at this problem from our bit of the science that we were interested in doing and not from actually developing a whole mission. So I think having that whole systems engineering capability, understanding the complexity when you put two pieces together and they do something completely unexpected and you have to start again to understand that behavior. So that would be my quick answer to that.
And David, I suppose from the testing side, you know, you obviously have got to get it off the ground and deployed, you know, in orbit. So can you give us a little bit about that, please?
Yeah, so of course you have to do a lot of testing. Before you even get to testing, you're writing so much documentation, right? Documentation is key. So we thought we knew how to build a spacecraft, and in some sense we did. You know, building the spacecraft was very much like we expected it to be. What was new to us was documenting it every step of the way. You need absolute traceability. If something goes wrong, you need to be able to look back and find out where it went wrong. And that's so that you get to a point where you're 100% sure nothing's going to go wrong. Yep. And that is absolutely key. So documentation and then testing. And the testing sort of trades off the documentation. You know, when you do testing and it fails, you look back at the document, oh, that's where that went wrong. That's what we need to fix. So you fix that and you go through it. And eventually you get to a point where you have a lot of confidence in your spacecraft. So launching, maybe I had a bit more confidence than Lorraine when we launched, but I had absolute confidence in the hardware that we had built and the software that we had written to run on that hardware, because it had been tested so much, and because all of the students who have been on the team went through that process of learning how to test, how to write documentation, and we could trust that all of the work they did was to the highest standard.
Fantastic. And you mentioned the team, so you obviously had an internal team. How many people do you think internally were involved in this, from concept to
So we
deployment?
have records at least of 50 students who worked on it, some maybe for a 3-month project as undergraduates, some like David who did their whole PhD and are now postdoctoral research.
Pretty cool PhD.
Exactly, so 50 students. There are 238 people's names etched on the spacecraft as well, and they're people who helped us along the way up to March last year, because we had to draw a line somewhere, so more than that since then, of course. A huge team effort, not just the people actually working on the spacecraft, but in the government departments and the funding agencies across the university. The health and safety officer was used to getting very strange phone calls and emails from me saying, can you get me insurance for a satellite, please? And so on. So, yeah, we really covered all bases, not just scientific, but, legal, administrative, safety, launch, procurement, dealing with the whole fallout from the launch that we should have been on. We should have been on a European launch vehicle, the Vega C, in March 23, and then that previous launch of that rocket had failed, and that put us in a position where we had no right to space anymore. And so it was quite a challenge then to understand how we would actually get to space, because part of the program we were in the European Space Agency is called Flyer Satellite, and they provide the launch for us as part of that program. But obviously we were stuck, and then that became unlocked last summer when the Director General gave his approval for us to go on a Falcon 9, which was a really incredible experience.
And you said it's very much an Irish team, so outside of UCD, I think you mentioned Bio, for example. I mean, can you tell me what sort of company, what companies were involved in and their participation in the mission?
So there's a surprising amount of Irish technology in it. So as you mentioned, Bio, who developed these coatings, Solar Black and Solar White. Solar Black has been in space before. It's on Solar Orbiter, a very famous mission, a really, really cool mission. And Solar Black protects Solar Orbiter from the sun. Solar White didn't fly on Solar Orbiter, but it's a sort of a newer version for different purposes. So we're testing that for the first time, and that was developed by Bio. And we worked very, very closely to make sure that the experiment that we were doing on EIRSAT was a very good test of their coatings. So there was a lot of engagement with them. On the Gmod side, then we have these very, very cool piece of technology called a silicon photomultiplier. So for years and for decades, really, in space, when you wanted to do a gamma ray detector, you built that using something called a scintillator, which sort of detects gamma rays and produces flashes of light, and something called a photomultiplier tube, which is a big vacuum tube. So it's kind of like going from a CRT television to a flat screen television. Now we've replaced this big vacuum tube with this little piece of silicon that can do the same job. And that was developed by Sensel, a company from Cork. And that's a really, really cool, really important enabling technology, not just for Gmod and for EIRSAT-1, but for all the gamma ray missions that are coming up.
Yeah. So you mentioned challenges earlier, Lorraine. I mean, can you give us some examples of some of the challenges you weren't expecting on the journey?
Sure. We had first to do something like this, we realized there was no equivalent of the Irish Aviation Authority, who looks after Irish airspace, aviation safety, and so on. There was no equivalent of that for space in Ireland. What has to happen if we wanted it to be an Irish satellite? You have to register your satellite at the UN, believe it or not. So who does that? The government does that. Okay, so you talk to the government. We don't know how to do that. Okay, we don't either. What should we do? Okay, we look into it together. And so that takes, a long time to get through that process, understanding what the pieces of the puzzle that have to go into making that happen. One of the pieces of the puzzle was a very interesting story. There was a 1967 treaty from the UN called the Outer Space Treaty, which Ireland had ratified. So that says, if we'll use space for peaceful purposes. If an astronaut crash landed in Ireland, we would repatriate them to their home country, etc. Turned out in 1967, when the civil servants went back to look at the records, there was no record that that had ever been debated in the Dáil. And what that means is that it doesn't have any legal basis for Irish enactment. So it had international force, but it didn't have any national force. So we actually had a debate in Dáil Éireann in July 2022 on the 1967 Outer Space Treaty, which was passed, thankfully. We were in the audience in the visitors gallery. That meant that there was then a legal basis for EIRSAT to be registered as an Irish satellite. I actually spoke to colleagues in UCD law about constitutional law, because in the Irish Constitution, if it's not mentioned in the Constitution, unless there's law in place, you can't do it. Apparently, in other constitutions, if it's not mentioned, then you can do whatever you like there. But ours is different. So this was all completely new territory. I had no idea about any of this. So we had to learn all this. We had to learn about spacecraft insurance, who's liable if the satellite damaged another spacecraft in orbit. The ESA experts told us we couldn't be found liable because we have no propulsion on board, so we couldn't move out of the way if we were on a collision course with another satellite. But the Irish government was being very cautious. This was the first time we've done this, so we had to get insurance, third party on orbit, just to be sure that if we did somehow cause damage, that we would be covered. So all of those other aspects were just completely no idea that that was going to take so much work and effort over the last 5 years. And COVID, of course, was the pandemic was a big issue for us. We had test campaigns planned in the Netherlands at ESA, and we had to make alternative plans for that because the schedule was still running. We were still on deadlines with ESA, but we couldn't make these tests happen in the way we planned. So we were able to creatively work around these.
David, have you any challenges that come to mind that you weren't expecting? I'm sure several.
Plenty. So, I mean, EIRSAT-1 is a complicated system, right? And that's why it's called systems engineering. It's like you're trying to put together this system. So it's got all these different parts, and it's very easy to get your head around one part. But you put those all together, and how do they interact? And that's when things get really, really challenging. So we spent a lot of time building things, and then we spent a lot of time building things that pretend to be the satellite to other things so that you can sort of test how it works. And then you have to put it all together, and they don't ever really work together the way they're supposed to work together. So you build all these things and you test them on their own, and you put them together and you test them, and that's not what it was supposed to do. Why did that not do the thing it was supposed to do? And that can be really, really challenging, because you have to go in then sort of like forensically and say, right, what happened in this interaction, and figure out why it didn't go the way you wanted it to go, and then figure out the fix. So there's been plenty of those, and some of them they pop up they always pop up when you least expect them, but sometimes they pop up quite late after you're like, I thought we fixed this, I really thought we had a handle on this. And it just turns out that you've not tested it in every single possible combination, and you've just randomly encountered a new combination or a new scenario, and you're like, well, I'm glad this happened on the ground and not in space, and that we had an opportunity to fix.
Yeah, and so the satellite is now in LEO, low Earth orbit. How long did it take to commission it once it was launched? Is it still in commissioning phase?
So it's still in commissioning mode. So we launched on December 1 from Vandenberg Space Force Base in California, and it almost on the first pass we heard from it via amateur radio enthusiasts across Europe, which was tremendously exciting. So we knew then that the critical things like the antenna had deployed, and that was one of the systems that was developed fully in-house that caused an enormous amount of pain to David and Joe, our chief engineer, because we didn't have a background in radio frequency, antenna design, all the grounding issues, all the noise that you can encounter. And this was a key component. If those antennas, which were curled up inside the small footprint, if they didn't deploy, that was it, game over. We had no way to communicate with the spacecraft and get data back and forth. So when that first signal came through the radio amateur community, and then suddenly comments, because they post on Twitter, on X, wow, incredibly strong beacon from EIRSAT. Like, oh, thank goodness, it was worth that pain that it's so strong and behaving so well. So commissioning is underway. First science data from EMOD 2 days ago.
Yeah.
Okay.
Yeah. So.
Yeah. So we've been working flat out for 6 years on this. We launched December 1st. Went into the commissioning phase. Everyone was wrecked. So we're like, okay, we're going to take it slow. The spacecraft's in orbit. It's behaving well. It's doing what it's supposed to. It's not in any danger. Let's just slow down for a little while. Take Christmas. We'll look after it. January, we're going to go and commission it. So that's what we started doing now. We're commissioning the science payloads.
Yeah. And the launch, when you're both actually there for the launch, can you talk us through that? That must have been really exciting and also terrifying, I would imagine. David, do you want to?
Absolutely terrifying. We almost missed it because what we didn't realize is we were watching the feed. So the launch pad is just over a hill, and the rocket is like just barely peeking out over the top of the hill. So you can't actually see the rocket on the launch pad. We were watching the feed. And what we didn't know is there was a little bit of delay on the feed. Mm-hmm. So this thing comes up, and we're like, oh my God, there it is. Absolutely incredible. You see this thing going up into the sky, and it's the flame from the rocket is so bright. Like, it's intense, it's incredible. And then after a couple of seconds, the noise from the rocket hits you, and it just washes over you, and it's so loud. It's just an incredible experience. And so we watched it take off. And the really cool thing about the Falcon 9 is it lands. Yeah. So 8 minutes later, we watched it land again. Wow. And when it lands, as it comes down very, very close, it's still going supersonic speeds. You get a sonic boom, and it is the loudest thing you have ever heard. It is so loud. Wow. And yeah, I think at that point, the tears just started flowing. Well, incredible.
The main payload on the flight we were on was a Korean spy satellite, so there was lots of cloak and dagger. You can't say what day you're going to launch, you can't say where you're launching from, you can't say what time. So we were being very cautious. But anyway, in the end, Dave appeared on Korean national TV as the crew did a pan around, and we were all cheering and very emotional. But it was an amazing experience.
Very emotional. We were all hugging each other. So there's this shot of myself and Joe Thompson, our chief engineer, hugging each other on the Korean news that you can go and track down.
That could be misconstrued by the Koreans, but we'll see. How long will the satellite last? How long will it deliver for?
Yeah, we're still working on the simulations, so we reckon between 2 to 3 years. So we'll see what I was noticing. We were talking to some projects outside, a team from Gonzaga, I think, who were doing solar flare monitoring and prediction. So, of course, the solar eruptions take an impact and a toll on the lifetime of a satellite. So we're very interested in that. But there's quite an uncertain range. We're getting about 3 years. ESA's getting about 2 years, so probably somewhere in between.
Okay, and is there an EIRSAT-2? Or what's the future plans? Do you want to go through it all again? Or
we have lots of plans. I'll let David talk about the study he's leading, but I suppose from Irish space sector point of view, it's our next step will be a big project that's been funded through the Disruptive Technologies Innovation Fund with 6 industry partners to kind of build on all the capability that we have now to support Irish businesses get their payloads into space.
Yeah, I'd say there's lots of EIRSAT-2s is the problem. There's too many, from ideas to projects that are actually quite far advanced and that we're beginning to build hardware for. So I don't know which one is going to be called EIRSAT-2 or if any of them are going to be called EIRSAT-2, but there's plenty of next satellites in the works. And yeah, as Lorraine said, I'm working on a study where we're looking at putting larger gamma ray detectors sort of derived from GMOD and using lots of other very, very interesting technology, but still in a CubeSat format, bigger CubeSats, and lots of them. maybe a swarm
Yeah,
of CubeSats.
absolutely.
Yeah.
And obviously, for the audience, I mean, is there an outreach program? Is there any way? I mean, one of the main things, I suppose, of this is to try and grow the capability and skills in the island of Ireland with the young people that are here at the conference and in the exhibition. I mean, how can schools and teachers get involved in this program?
Yeah, that's been really important to us from the beginning. So we've always done, lots of school visits and so on, space careers roadshows, etc. But I think what's great now is the huge interest from teachers, so much so that we have with the IJA group in the Department of Education, there's a whole learning path for junior cycle and senior cycle on skullnet.ie. So there's a learning path for EIRSAT-1 there, in particular on radio communications, on Python programming for, how to look at space debris, so building rockets, all sorts of activities and curricula going on there. We also have a 3D printable version of the spacecraft, a very high fidelity model. So if you have access to a good 3D printer in your local library or in your school, that could be an exciting project, but it's not for the faint-hearted. I think there's 90 pieces to that, and a beautiful instructional video and manual. So if that's a bit too much, there's a paper model as well, we call Origami 1, so you can print that out just on your regular printer and cut and tape it together. So I think for us, it's and this radio comms activity, if you have in your school microbits, you can use those to simulate the comms that we have between our ground station and EIRSAT. So please do have a look at our website on the Get Involved page if you're interested in hearing more about that.
Fantastic. And can I just ask, with the European Space Agency, do you think it's strengthened the relationship with Ireland or with ESA, or impacted it in any way with the government, or what do you think the heritage from this will be?
Absolutely. Our relationship with ESA, I mean, basically the people at ESA who have worked on this project, we consider them EIRSAT-1 team members. The way that we work together, like we were practically the same team. So I think that's been a fantastic relationship that we've had, and it's really, really strengthened during the course of the project.
Yeah.
It was in November last year, there was an event at ESA in the Netherlands for EIRSAT-1, so we were all invited over for a celebration, and they invited the 70 ESA experts who have supported us through the mission. So from all the different departments of ESA, from the legal, from materials, from thermal analysis, from electronics, from optics, you name it, as well as these education people who are our core contacts. So more than 70 people have interacted with us throughout the mission and given us their expertise and guided us to this successful endpoint. So I think it's been a game changer for our relationship with ESA. Everyone in ESA knows about EIRSAT-1 now, much to my surprise. Yeah. It featured in the DG's end-of-year highlights, and so it seems to have taken on quite a lot of momentum and excitement in ESA because of the fact that it was student-driven. I think that was very exciting for them, and they are very keen to promote space in all the member states, and this was a good example.
No, I think it's fantastic what you guys have achieved, and I'm sure everyone in the audience would congratulate them with us here. Yeah. There is an opportunity here if anybody has any questions from the audience. So I see these. Okay. So there's one. So we're going to let this young gentleman here. So hang on a second. We're just going to be recording this, so I want to catch you on the microphone.
I was just wondering, is any of the code open source, or how does it work? Like, can I have a look at the code myself, or?
Not a lot of it is open source, unfortunately. So the main computer that we is on EIRSAT, the onboard computer, that's running code from a UK company. So they make what's called a flight software development kit. So it's an SDK for your satellite. So we purchased that, and then basically that was the starting point. And then we went from there. We built a lot of software on top of that, but unfortunately the code base is closed source. And I mean, we really would love to release as much as we could openly, but we're somewhat restricted in these things.
Grant, thank
But
you so much.
if you're interested in listening to EIRSAT-1's beacon and decoding it, the code for that is on GitHub repository.
Yeah. So if you do a search for EIRSAT-1 beacons, it's the first result on Google. You'll find a GitHub repository that tells you how to decode and get all of the information that EIRSAT-1 is sending down and see what it means.
I look forward to your young scientist participation next year. Please.
Hi there. You mentioned that after the ESA's Vega C rocket didn't perform as expected, you were forced to kind of switch to SpaceX's Falcon 9. Did that bring up any issues with, like, did that follow your optimal orbit? Like, you must have had a plan, you must have had an idea of where you wanted to go, but because of the switch, and of course the priority was for South Korea's spy satellite, so you must have had to make some adjustments, or were there any benefits to the unexpected switch?
Absolutely, yeah, you're absolutely right. So basically, when we found out, basically how these things work is you go to a launch broker and you're like, do you have any launches coming up? And they're like, yep, here's what we have. And they tell you what the orbital parameters are going to be for the launches that they have available, and then you have to see if that's going to, work with your mission profile. And in a lot of cases, it's slightly different to what you had planned. And then you have to do a lot of analysis to figure out, is this actually going to work? And that was one of the challenges and lessons that we learned, is to, when you're doing your analysis, sort of make it in a way that you can plug in these new parameters, so try and, you're going to have to do it again. So make it as easy as you can for yourself for the second time and the third time and probably the fourth time. Yeah.
So, but for sure, we always knew we were a rideshare passenger, so that we weren't going to have much control over the mission, the launch. We were just going to have to take whatever we were given. So when Vega C failed, there was a proposal at one point to move us on to an additional Vega flight that was brought in and actually went up last October. And that was going to be to a much higher altitude, probably 580, 575, something like that. And you might think, well, 525, 575, what's the difference? The difference would have been a 13-year lifetime. So the educator in me is like, yes, more years in space to teach more students about spacecraft operations. And then the legal insurance person, half of my brain was like, oh my God, we'd have to pay insurance costs for 13 years instead of 3 years. So there was, so there was all of that. So we had to go and actually get backing for a potential 13-year lifetime when that was on the table. And then that went off the table again because the capacity of the Vega was much less than Vega C, so we were bumped off it basically. So at that point we were really beginning to feel a bit forlorn. Last summer it was a bit of a dip in the morale of the team, as you can imagine. So we did push very hard for Falcon 9, and we knew once ESA launched its Euclid mission last July using the Falcon 9, that was a game changer for us, because now we weren't going to be the first. They had done it for a major science mission of the agency, so it was probably less of a hurdle for us to be accepted as a passenger. But as I said, we didn't really get much information as to the orbit we were going to end up in. We got a very, very large range of values, but we knew we would have enough power to communicate with that altitude. We knew the thermal environment was going to be okay. So as David was saying, by that stage it was more routine to run these simulations because we'd had to do it so many times.
Thank you very much. Thank you.
And if you want to pass the baton next door, go ahead.
So the satellite size, packing all the different things into such a small size compared to satellites, as you said before, complete different, bigger size of all these other ones. Did that affect the quality of different abilities that the satellite could do, or did it force you to remove some abilities, such as you said, mobility is completely out of the question now?
So I'd like to say it didn't affect the quality. Of course I'm going to say it didn't affect the quality, but it definitely made things more challenging for sure. But it kind of worked well for us in a way, right? Because it's it's always easier to work to a constraint. You know, if you have a challenge, it's kind of easier to work against that rather than like, here's a blank piece of paper, do whatever you want. It's like, oh God, what do I put on the paper? And what we're sort of looking for in the future is to make gamma ray detectors, to make observatories in space that might be quite large, but we want to make them as efficient as possible, right? So that means packing in a lot of technology, even into those big satellites, so they're going to become very, very dense in terms of the instrumentation. So for EIRSAT-1, that was like a challenge to pack part of one of those satellites into EIRSAT-1 and to make it as small and as densely packed as possible, and to sort of prove the technology for the next generation of satellites.
Super. Well, folks, I think that's out of time. I think I want to thank Lorraine and David for a very inspirational presentation and walking us through EIRSAT-1, Ireland's first satellite. I think it really is going to be the beginning of something massive for Ireland in space, and I think you should be very proud of your achievements. So thank you very much. Thank you very much.
Thank you.